that change. So we're going to look at some properties of polynomials and what they mean about what the graphs are going to look like of polynomials. So we're going to look at how do we sketch graphs of polynomials. Let's get all earbuds and stuff away. I need your undivided attention here. But I promise I'll make this. We won't do this all period. We'll make this relatively short. If we want to graph something in math, we're going to use Desmos or a graphing calculator. We're not going to graph things on graph paper. We're going to sometimes sketch graphs on graph paper or on or it doesn't even have to be graph paper. If we just want to kind of get a rough idea what it looks like, that's what we're going to be doing, is sketching some polynomials in this section. All right, so if we look at this polynomial function, that looks terrible, right? That looks really scary, but it's not meant to be. All this means, this is just sort of a general mathematical way of saying that a polynomial is just a sum of a whole bunch of terms. And in each term, notice there's an a in each term, and then there's an x. There's a power of x. The a just means a coefficient. It just stands for a number. Why do I call this, instead of calling it a and b and c, why do I call it a sub n? That's the way we say that in math. When you have a subscript, you'd say a sub n minus 1, a sub n minus 2, all the way down to a sub 2, a sub 1, a sub 0. Okay, the reason we do that is because we're trying to link up the number that goes out in front, the coefficient, with whatever the power of x is in that term, right? So to keep this totally general, we're not saying that the biggest power of x is 3 or 4 or 10 or 20. We're saying it's n, right? So it could be anything we want n to be. But n is going to be the biggest power of x, and then the next term would be one less than that. So if n is 25, then the first term is going to have an x to the 25th. The next term would have an x to the 24th, 25 minus 1. That make sense, what we're doing? So really, this is the thing we're doing. We're trying to match up that, trying to match up that with that. Okay, that's the only reason we have that subscript there. Okay, so what we really care about here is that if we write this thing in standard form, we know that the biggest power of x has to go first when we write it in standard form. So we say that the term that has the biggest power of x is called the leading term. Okay, I want to write that down. That's the leading term. How come? Because it leads things off. It's the first thing we write down when we write the polynomial in standard form. So if that's true, then whatever the number is that's being multiplied by x, which is we're going to call a sub n in this case, that is what we call the leading coefficient. What's that mean? It just means whatever number is being multiplied by the biggest power of x. That's the leading coefficient. Okay, so let's practice just identifying what these things are a little bit. This is really just vocabulary stuff. Okay, so let's start off with this first example, f of x equals 4. Now going back to what we talked about, when was that? I guess it would have been earlier this week. No, maybe it was last week. Can't remember. What did we say the degree of that function was? What did we say the degree of that function is? Let's start. This might be easier. What's the degree of that function? 1, right? Because it's the biggest. What is the power of the biggest power of x? Well, there's an invisible 1 there, and so the degree is 1, right? What's the leading coefficient of that polynomial then? Not 0. -5, right? Because all we're asking is what's the number that's being multiplied by the biggest power of x, right? So in this case, it's just going to be that number right there. So the leading coefficient is -5. Okay, what's the degree of that top function then? 0. Good, because x doesn't even show up, so it must be taken to the 0 power. So the degree is 0. This is kind of a weird one, and really we wouldn't even think about that as being a polynomial, honestly, except in this one case. What's the leading coefficient then? What's the number that's being multiplied by x to the 0? 4. Yeah. That one's a little bit weird. This one's more normal. Third row. What's the degree? 2. What's the leading coefficient? 12. Next one. Next row down. What's the what's the degree? 3. What's the leading coefficient? -1, because I've got that negative in front of the x cubed. Give me thumbs. How are we doing? Okay, let's try one more. Let's try this bottom one. What's the degree of this bottom one? 5. What's the leading coefficient? 9. Okay, we got it. Good stuff. Okay, so let's practice identifying some stuff just a little. This is like one of the questions you'll see on your homework, for example, or on the test. So the leading term of the polynomial here is what? So not the leading coefficient, the leading term. It's going to be that whole thing. The leading term is just the first term in the polynomial, right? What's a term? Terms are the things that are added or subtracted. So how many terms do I have there? I've got 1, 2, 3 terms. Leading term is just the first one, okay? So now, what's the leading coefficient? -1/2. In the leading term, it's just what's being multiplied by x. What's the degree of the polynomial? 3. Okay, and then just a little reminder here from the other day. What do we call a polynomial that has a degree of 3? Cubic. There we go. We call that cubic, right? Okay. All right. Yes, thank you. Okay. Okay, so what about this one then? Now we're looking at the basic shapes of these polynomials. And I want you guys to kind of think about, like, if I graph the simplest possible parent function for a constant polynomial, that would just be f of x equals k, or even simpler, we could even just say f of x equals 1. Everybody agree, y equals a number is just a horizontal line, right? Okay. What if we do the simplest possible linear polynomial? That's going to be f of x equals, we'll pick a monomial, right? Make it as simple as possible, and let's make the leading coefficient 1. So that would just be f of x equals x, or x to the 1, right? Well, what's that look like? Y equals x is just a line with a slope of 1 and a y-intercept of 0, right? Okay, if we kept going, well, we're familiar with this one too, quadratic. If we take the simplest quadratic polynomial, that's just going to be a monomial with a leading coefficient of 1, so f of x equals x squared. And we know what that looks like. It's just a really simple parabola, right, with the vertex at the origin, okay? Cubic function, now we're getting into some newer territory. If we do a cubic function, f of x equals x cubed, it looks kind of like a quadratic function. It starts off sort of like a quadratic function, but instead of going up on the left, it goes down, right? And from there on out, you notice things look pretty similar. If I take a quartic function, it looks an awful lot. So f of x equals x to the 4th. That's our simplest quartic function. It looks an awful lot like a parabola. The only difference is it's just got steeper sides, and it's got kind of a more squared off base. What about a quintic function? That's x to the 5th. Well, again, it looks an awful lot like x cubed, only it's just a little bit more squared off. It's steeper and it's more squared off, but it otherwise looks the same. If I go into Desmos and I just make a whole bunch of these, you're going to see a pretty obvious pattern. Yeah, and you probably already see the pattern, yeah. Actually, I'm just going to make these y's. So y equals x squared. If I do y equals the next even power of x, I get y equals x to the 4th. Look, pretty similar. if I do y equals x to the 6th, it's just a little bit more squared off, but it looks pretty similar, right? What if I do, make a really bold prediction here. If I do y equals x to the 100th, what do you think it's going to look like? It's going to be like a parabola, but it's going to be really steep sides and really square, right? If I'm doing even powers, the only thing that's changing is they look basically like x squared. They're just getting steeper and more squared off, right? So if I do y equals x to the 100th, man, that looks pretty square, right? Okay, but they all have something in common. What kind of symmetry do all those curves have? How would you describe it? Like if I look, I'll just pick one of them. Yeah, you could. If you want to use a biology term, you could say bilateral. I think I know what you mean by that, though. What's a way I could, I don't want to say this. Like if I had a piece of paper, how could I demonstrate, let's say this were graph paper, how could I demonstrate the symmetry of that green function? What could you do? You could fold it in half right along the y-axis, couldn't you? If I put the fold right along the y-axis and I folded this thing, so there's my crease and I folded like that, wouldn't they just line up perfectly? So it has line symmetry or folding symmetry, right? And we explored that when we looked at parabolas, right? They all had that line of symmetry. Okay, now let's change these a little bit. Instead of even powers, let's do odd powers, and let's start with x cubed. So there's x cubed. There's x to the 5th if I go up by 2. Again, it's just a little more squared off, right? So now we'll make this x to the 7th. And if I make x to the 101th, what do you think that's going to look like? It's going to be pretty squared off. Is it going to go, okay, so now is it going to go like that? No, it's going to go like that, isn't it, right? Okay. There it is, right? Pretty squared off. Okay, again, let's just go back and pick one of these. They all look basically the same. So what kind of symmetry does that have? It's a little bit different. It's not folding symmetry, is it? There's no way to fold this paper and make those things overlap. But doesn't it look like there's some symmetry there? There is some, right? I mean, definitely, don't the right and the left halves of that function look pretty symmetrical? Say it again. I could rotate it. Yeah, exactly. If this is a piece of graph paper, couldn't I put a tack right there at the origin and spin that thing 180 degrees and they'd line up perfectly, right? Okay, so when we have odd powers of x, we know that those have rotational symmetry, right? But for now, we're not even so worried about the symmetry. I wanted to point the symmetry out because we'll come back to that. But what we really want to see is what's happening at the ends of the function. For all of the odd functions, if an ant walks to the right forever, he's going to climb up towards infinity, right? If an ant walks to the left forever. So in other words, we could say as x approaches negative infinity, as the ant's x coordinate approaches negative infinity, he's going to go down forever, right? Compare that to an even function. The even function was different. Even function, if I went to the left forever or the right forever, in either case, the ant goes up forever, right? So the end behavior is up on both edges, right? Both ends of the function. Okay, so hold that thought. So then there's a really easy way for us to predict what any polynomial, what the end behavior of any polynomial is going to be, right? All we have to do is look at the leading term. That's it. If the leading coefficient is positive and the function has an even degree, 2, 4, 6, 8, 10, 100, whatever, what's the shape of the function going to be? Whoops. It's always just going to look basically like that, isn't it? Might be more squared off, but it's going to be up to the left and up to the right. Okay? What if it's an odd degree function? What's it do? That's the one that looked kind of like it was up to the left, or to the right and down to the left, correct? Okay, now what happens to a function if I have a negative leading coefficient? Let's just explore this really quick with Desmos. What's going to happen if, where is this? So like if I took, for example, let's just make this really easy, make it x squared. And if I have a positive coefficient, like if I multiply that by 2, all it does is it just changes it stretches it out a little bit vertically is what it does, right? But it doesn't change the end behavior. It's still up to the right and up to the left. What if I multiply that, my x squared, by negative 2? What's it going to do? It's going to flip it. Okay, so if the leading coefficient is negative, it's going to flip this around, so the end behavior has all been flipped. It's going to be down to the right and down to the left. So we know negative leading coefficient and even degree, always the end behavior is always going to look like that, down left and down right. Well, I bet you could make a prediction here. If I have a negative leading coefficient and an odd degree, what's going to happen? So when I go to the left, is it going to go up or down? If I have a negative leading coefficient, it's going to go up. When I go to the right, it's going to go down. Yeah. So it's going to look like that. Okay. All right. So what we want to do here on number 7, all I want you to do here on this one is I want you to determine what's the sign of the leading coefficient and whether the function has an even or odd degree. Okay, now here's the thing about this. We don't care what's going on in there. All we care about on this thing is what's going on with the end behavior of the function. In between, we don't care. So in other words, this one, how would you describe it? The left end behavior is up or down? Down. Right end behavior is down. So what's that tell you then? Even function, what positive or negative leading coefficient? Be negative, wouldn't it? Because it's got to be that guy. Negative leading coefficient, even degree, right? Okay. Okay, how about this one? What do you think for that one then? Positive leading coefficient, odd. There you go. It's positive odd, isn't it? Okay. Because it's going up to the right and down to the left. There you go. Okay. So then, what about this guy? What about this one? I'm not giving you a graph this time. Okay, it's going to be a negative even, isn't it? Okay, so now what's that mean then? Let's put this in a slightly different, use different terminology. This is the kind of terminology we'd use in calculus. We'd say as x approaches infinity. That's what that's saying right there, is x approaches infinity. So what's that mean? Think about your ant on your graph. Where's the ant going if x is approaching positive infinity? Now x is the horizontal variable, right? So if the x coordinate on our function is approaching positive infinity, what's that telling you? What direction is he walking? Okay, Peyton's right. He's going to the right forever then. He's going in the positive x direction infinitely far, right? So he's going out that way as far as he can go. We're asking the question then, what is f of x? F of x is just a fancy name for y. That's the vertical variable. What is the y coordinate? What's the function going to approach? Meaning, what's the y coordinate going to approach? If it's a negative even power. If he goes to the right forever Is he going up or down? Down, because it's a negative even, right? So it's the function's going to look like this, right? It's going down on both sides, right? So then that means, what are we going to say? Well, f of x is approaching negative infinity, right? So it's going to be that guy, agreed? That's what's going on. That's what the function's doing. So f of x is approaching negative infinity is the answer, right? It's going down towards y equals negative infinity. Whoops, did that backwards. That goes up here, doesn't it? Yeah. Okay. Now, what about the other direction? As x approaches negative infinity, what's that saying? The ant's going where? Left forever. What is f of x or y approaching? Down forever, right? It's going down forever. So, again, it's going to be this case where it's going down forever, so it approaches negative infinity, right? Give me 1 to 5 on that. Is that making sense? Okay, good. Okay, one more and then we'll quit. This will be it for today. How about this one? So how would you describe this? Negative odd. So then what's the look for negative odd? Okay, so it's going like this, right? One of those things. Yeah, okay. Okay, one of those guys. We have 1 minute left. Okay, we're done. Oh, no, then we got to finish this one. God, Gage, dang it. Okay, so then if it's doing that, as x approaches infinity, so as we're going to the right, I'm pointing with my left hand, but you guys see it as right. If we're going right forever, what's y doing? It's going down, right? Do that, you want to see that again? Okay, so then what's the answer? F of x approaches negative infinity. Y is going down, right? Think what y, that's positive for y, that's negative, right? So as x approaches negative infinity, now what's it doing? It's going up. There you go, right? One of those guys. Okay. So the answer is positive infinity, right? Good? Give me 1 to 5. How we doing? Okay. We'll call our quits there. That's pretty good.